So this morning, I'm very pleased to introduce our fourth plenary speaker for the 2020 SIAM Life Science online meeting. It's Sara Del Valle. So Sara is a senior scientist and mathematical epidemiologist at Los Alamos National Laboratory, where she leads the fusion team. Her work combines internet data with satellite imagery to forecast disease outbreaks, some ideas that I found novel and really fascinating when I looked into them and read about them. Her work is extremely topical these days, in case that's not obvious. She's studied the economic impact of pandemics, including the mitigating influence of face masks during the 2009 swine flu pandemic, and more recently has been focusing on the spread of COVID-19 in the US. And given what I know from my Canadian colleagues working on COVID-19 modeling and attempting to guide policymakers in these unusual times, perhaps a bit more unusual in the US these days, I'm sure this is a very busy time for her, and we're very grateful to have her here with us this morning. So with that, I will pass the screen on to you, Sara, and hopefully you can work your slides up to present them.
Okay, sorry, I just needed to unmute my phone before I shared.
Just one quick reminder for everybody. Sorry about that, Sara. So the talk will run about 15 minutes and we'll have about 10 minutes at the end for questions. And we'll do that through the chat. So if you have questions, you can put them in the chat as the talk goes on. And please, if you do have any control over your mic, please make sure your mic is off. Okay, thank you. And Sara.
Okay. Yeah, thank you so much for the invitation to be here. And I feel like it's really exciting to be talking about mathematical model for infectious diseases, given the current state of our nation and the world. And I'm excited for many different, I'm excited and I'm sad at the same time for many different reasons. I'm excited because mathematical models have actually played a key role in understanding, mitigating the spread of coronavirus around the globe. And you've all seen many different articles and news reports about how infectious diseases are actually playing a major role in this pandemic. And so that's exciting. I'm also excited because the whole research community has come together to help fight this pandemic. And I hope that this will continue and that these collaborations that we're making and we have been making will continue in the future. And I'm also excited because I hope that this will encourage many students and girls and people that that didn't really know that mathematics could actually be used to understand infectious diseases, that they could hopefully join our community and use mathematics to fight pandemics and to fight many other different infectious diseases. So it's exciting. It's also sad that obviously that we had to come together during a major pandemic that is causing a lot of impacts and it's, and thousands of people are dying, but hopefully we will change that in the future. Okay, so now let me start with my presentation. So first I just kind of wanted to give you an outline of what I'm gonna talk about. I want to start with a very brief history about pandemics and also history of epidemic modeling. And then I'm going to talk about 3 specific examples of how we're using real-time data fusion for disease forecasting applied to influenza, dengue, and COVID-19. And then at the end, I'll just conclude with some remarks. So here's a kind of a very brief infographic about the history of pandemics. And as you can see, humans and diseases have coexisted for as long as humans have been on this earth, and many millions of people have died from many of these diseases. And I don't know if you can see, but basically there's the death toll of each of these diseases. It's kind of shown there along this graphic. And it's specifically, I think the 1918 pandemic, it's believed to have caused like 50 million deaths worldwide. So clearly pandemics have, are a major problem, and so understanding them and figuring out how to mitigate them is important. Thankfully, Thankfully, there's been some major breakthroughs and discoveries that have been able to mitigate the spread, from vaccines, and especially the smallpox vaccine that was critical in eradicating smallpox. And now we have many childhood vaccinations that have made a tremendous change in how infectious diseases is spread. Obviously, germ theory, genetics, antibiotics, X-ray, and I'm obviously just highlighting a few, but there's been a lot of different discoveries in medicine that have changed the course of how diseases impacted humans. However, I think we're at a tipping point where we can add one additional discovery or breakthrough in this list of discoveries that have been made. And the one that I want to propose today is real-time disease forecasting. So we're all familiar with weather forecasting, and before I've been working from home for some time now, and I remember that when I used to go to work, the first thing I would do in the morning was check the weather to see what I needed to wear, if I needed to bring a sweater too, or if I needed to bring an umbrella. And what we don't really know is, what happens behind the scenes in terms of weather forecasting. And so basically, in a very simple terms, weather forecasters use observation. So a lot of data from many different sensors, from, ground sensors, aircraft, satellites, ships. There's all kinds of sensors all over the world that collect data, and that data is combined with mathematical models that describe how weather works and the physics of the atmosphere and turbulence and winds and all that kind of stuff. And what you get is basically a probabilistic forecast for hurricanes, with a cone of uncertainty, or even just on our weather apps, we can see if there is a 25% chance of precipitation on that day. And we feel that that same approach can actually be applied for infectious diseases. And I'm going to show you how we have been applying that same approach. So there's a lot of different data that is collected from, satellites, social media, hospitals. A lot of clinical surveillance data is obviously part of that. Real-time, voluminous, extremely noisy data. We can combine them with mathematical, statistical, and computational models to provide probabilistic forecasts with quantified uncertainty. And many of you have probably seen a lot of these forecasts for COVID-19, and I have the link for our website where we're publishing COVID-19 forecasts. And so this is something that I feel like it's no longer an application or an approach that should only be applied to weather, but now we can extend it to infectious diseases. And obviously we're using it for COVID, but we feel that this approach can be used for all diseases around the globe. And if we are all able to understand what is spreading in our communities, people will be able to take the necessary precautions to hopefully mitigate their probability of infection. And we can hopefully together mitigate the spread or at least mitigate the burden around the globe. So I wanted to emphasize the difference between forecasts and projections, especially because a lot of people have probably been seeing these two terms used a lot in many articles and in the news. And so there's a fundamental difference between forecasts and projections. Both of these approaches can help mitigate the spread of diseases, but for this particular talk, I'm going to be focusing on forecasts. And forecasts are basically an attempt to predict what will happen based on current trends, whereas projections attempt to describe what would happen given certain hypotheses or what if scenarios. And I'm citing a paper by Masad and others that actually goes into more detail about this differentiating forecast and projection. So I encourage you to go in and check it out. Okay, so I kind of wanted to just give you a brief history of epidemic modeling, because I've been hearing from news reporters that many people didn't really know how mathematics were used and played a very important role in understanding infectious diseases. And I think this has been ongoing for a long time. And so I kind of wanted to kind of just give you a brief, just one slide of the history of epidemic modeling. And there's evidence that, and I think I have that date wrong for John Grant, there's early evidence that since the 1500s, people have been using, different kind of ways of understanding diseases using mathematics. And John Grant published weekly reports on mortality data and causes of mortality. And then he tried to give a risk of dying from a certain disease based on what people were dying from. And so that was one of the earliest recordings of the use of mathematics for infectious diseases. And then going forward, John Snow is one of a very, I think, well-known study, and at least in the mathematical community, where John Snow was basically took a lot of the cases, cholera cases in London, and did some spatial analysis where he mapped all the cases of cholera, and he was able to pinpoint the cause of cholera to a water pump in Broad Street in the middle of London, and he realized that that's what was causing cholera for the people that were actually getting water from that pump. And then, in the more quotes unquote recent, in the 1900s, Kermack and McKendrick were the ones who introduced this epidemic model, or SIR model, that you've all probably heard a lot during COVID-19. And this is a very neat and simple model that describes the way diseases are spread. And basically you have a system of nonlinear differential equations that describe how people move from the susceptible class to the infectious class to the recovered class. And the rate at which people will move from the susceptible to the infectious class is dependent on the interactions between a susceptible and infectious person. And so that's where the nonlinear term comes from. And, but then that lambda term is also dependent on, we have, like, in this case, I'm showing the contacts, and then this beta, which is a transmission. And the transmission encompasses different things, such as the susceptibility of the person. So for example, if for COVID-19, it seems like elderly people are more susceptible. So then then you can, increase the susceptibility for that age group. And then the infected person also, the transmission rate also encompasses the transmissibility or the infectiousness of the infected person. And this model can actually be extended into age structure. So you can add, instead of just having one susceptible class, you can have age, and you can have gender. You can also break the model to incorporate people performing different activities. So for example, people who don't wear masks, you can make them into a non-mask wear kind of compartment, and then you can add people who wear masks into a different compartment. And all of this can tell you how diseases are spreading in a population. And then if you entered, if you use some initial conditions for this particular model, then you can see how the disease would spread. You have the susceptible class declining, you have an infectious curve shown in red, and then the recovered class in blue. And so basically, this is the simplest model, but even more complicated versions of this model can have similar dynamics of disease. So now I'm going to start on the first application that I described in my outline. I wanted to talk to you about how we are doing real-time flu forecasting, and then show you how we are using different data sources and different mathematical models to give us this probabilistic forecast with quantified uncertainty. So I don't know if many people knew, but the CDC has been interested in forecasting the flu for a while. Since 2013, they've launched a flu forecasting challenge. And I think they picked the flu for many different reasons. One is, we have it every year. So if you can keep trying and developing models and hopefully improving your models to see if hopefully if that your model can improve in its accuracy every year. We also have a lot of data, and flu is fairly well understood within the research community. So I think that was one of the reasons why it was chosen to be one of the first diseases to be used for forecasting testing. So the structure, basically, it's the challenge starts in late October, it runs through mid-May. They released the data, which is influenza-like illness data, or ILI. They release it every Friday, and the forecasts are due on Monday. So through October, from October through May, you have to submit a weekly forecast for the flu. And sometimes it can be challenging because you also have to submit it even if it's Christmas, during the Christmas break or the Thanksgiving break. But anyway, that's aside. And so the results are announced in August. And so they've decided to come up with different targets. And basically they have 3 seasonal targets and 4 short-term targets. One is the season onset, and this is basically the week when the ILI data is at or above this baseline, and the baseline is shown as a dotted line. So when the ILI data has been there or crosses that line for at least 2 weeks, then that's when you have to forecast that, starting in October, when that's going to happen. They also want you to forecast peak timing. So basically the week when ILI net will be the highest for the whole season. And they also are interested in the intensity, and basically the intensity is the highest value that the ILI net will reach. And then there's 4 different short terms, and basically they want you to forecast the intensity, for 4 consecutive weeks, basically. So if you submit it, it's for like the next week and the next 3-4 weeks. So we started participating in this challenge since 2013. And, one of the first things you do is basically you try to fit an SIR model to the data. And first, you use basically past data and to see how well your model can do when you try to fit it. And one thing we notice is that there's basically systematic deviation between the ILI data and the best versions of the SIR model. And so you can see I'm showing the epidemic curves for 2011, 2012, 2013, 2014, and 2015. And so if you were using an SIR model to participate and you wanted to know, the peak timing, clearly you can see that your model was not going to be able to capture that, because it does capture the overall trend. It's an epidemic that goes up and down, but it doesn't really capture the structure basically of the flu ILI data. So what we decided to do, given that the SIR model alone could not reproduce ILI data. Oh, and one other thing that I forgot to mention is that there's also systematic discrepancies there's systematic discrepancies in the data, but also one of the things that we also notice is that, so I'm showing week 13 with a red dot, and then week 14 is shown with a blue dot. And you can see that for every single season, week 13 tends to be higher than week 14. And that was just like something kind of unexpected, but the SIR model obviously wasn't able to capture. So what we decided to do is to use a Bayesian hierarchical model that has three main components, and one is the data, which is the ILI data that is provided by the CDC. The second piece or ingredient in our model is the process, which is a disease transmission model motivated by the SIR model. And as you saw before, I mean, it does capture the overall trend and dynamics. And so we wanted to exploit that. But then in addition to that, we decided to use a discrepancy component, which is a flexible function that captures the systematic deviation between the data and the process, basically. And the way we model this, the discrepancy is basically the sum of two terms. You have mu and delta, and basically mu captures the week specific discrepancy common to all seasons. And so basically this is, the mu is capturing this, what I described before, how week 13 is always higher than week 14. And this seems to be consistent across all the flu seasons. So then that's the mu component. And then the delta captures the week and flu season specific discrepancy unaccounted for by mu. And so obviously every season will have nuances that are not really captured by mu and that have not been observed in the past. And so then those are captured through the delta. And both of these pieces are actually modeled through a reverse random walk. So when you put all these pieces together, then this is basically what you get. And here I'm showing the posterior distributions for week 5, which is the first column on the left, then week 13, week 21, and then week 29. The bottom is just showing you the discrepancy terms for each of those weeks. Then the middle part is showing you the process data, which is an SIR motivated model for all these different seasons. And then at the top, you have the future, basically our forecast that kind of combine the process and the discrepancy to give you a posterior predictive distribution. And so you can see, so there's open circles, and that's the actual data that we had. Then the black circles are the data. And then in the top, you can see the solid line is showing you our median forecast, and then the 95 prediction bands around it. And you can see that at the beginning, there's a lot of uncertainty in terms of what's going to happen during the flu season. And because most flu seasons have 2 peaks, that's why you can kind of see that our model is suggesting that you're probably going to have 2 peaks because that's what's happened in the past. But as you get more data, so now when you see week 13, then you can see how the predictions bands are kind of collapsing around the median forecast. And you can see how the model adjusts for every week when we get more data and we know what's happening, how the flu is spreading, then our confidence starts to increase. And so our confidence intervals start to converge. And so we do this for all the US. So every state, we push a forecast. And then here I'm showing you the different forecasts that we submitted for 2017, 2018. And you can kind of see how the model was kind of adjusting as the epidemic was progressing. And the more data we were getting, the better, obviously, the forecast was getting. And so, but there is a problem that I haven't really addressed, and this is the ILI data. So here in Y, I have the data that we get from the CDC. And then the phi is basically the function that combines the process and the discrepancy term in our model. And obviously you're using these 2 pieces along with the data to forecast the flu. But what the CDC releases every Friday is actually what happened a week or two ago. They don't really tell you what happened that specific Friday. And the reason behind that is because there's this all bureaucratic process. They're getting a lot of data from hospitals and clinics and labs that sort of capture how the flu is spreading in different communities. And then they send them through this bureaucratic process that can create a 1 to 2 week delay before epidemic modelers can get the data. And so thankfully, we have an additional data source that can actually help us mitigate this problem, and that's internet data. And as I was showing at the beginning, how we're trying to exploit different data streams with models to provide a probabilistic forecast, we can do the same thing in this case, and we're using Google Health Trends. And it turns out that it's an actually viable solution, because many people nowadays are going to the internet to diagnose themselves, and they're also so we can track how internet search behavior and diseases are actually they correlate with each other. And we have published several papers that describe how people going on Wikipedia to find information about flu or dengue or tuberculosis in Chinese actually correlates with incidence. And here I'm also showing on the right dengue in Brazil. So then because we are able to get internet and data in real time, then we're able to actually fill one more circle in our model so we can use internet-based data to help us more accurately forecast the flu. And so here I'm kind of showing you the role of internet data on disease forecasting. On the top, I just have a graph that doesn't have internet data. It just has the black circles are observed ILI data. The open circles are unobserved ILI data. And then the solid line is our median forecast, and then the confidence intervals. And so you can see that by adding in 2 additional points from Wikipedia, in this particular case, we were able to not only increase the accuracy, because you can see that our median forecast in the top was like way off from actually what actually happened. And at the bottom, because we had additional internet data, then we were able to increase the accuracy and also reduce the uncertainty in our forecast. So, so basically we are trying to use both different types of mathematical approaches and different types of data to help us forecast the flu. Now, my second example is going to be forecasting dengue. Flu is obviously transmitted from person to person, and so I also wanted to give you a different transmission route to just kind of show you that this is actually possible for many different diseases. So dengue is transmitted through mosquitoes, and basically people cannot transmit dengue to each other. It's, the vector is the mosquito, and so when people get bitten by a mosquito, and if the mosquito was infected, then it will infect the person. And then, or if a mosquito bites a person and that person had dengue, then the person can transmit dengue to the mosquito, and that's the cycle. And so for this particular case, we have been using different data sources from clinical surveillance, satellite imagery, climate, demographic data, Google search queries with statistical models to provide probabilistic forecasts for dengue. And I will describe in a little bit more detail why we need to use more data sources to study dengue. And the major reason is obviously because mosquitoes don't tweet and they cannot go online. But the one thing that is very important about mosquitoes is that they need water to survive and lay eggs and reproduce. And so we decided to start looking at satellite imagery, because if we are able to capture green vegetation in a certain area, that means that there was probably precipitation. And if there was precipitation, then it's very likely that there's going to be standing water. And if there's standing water, then that's the perfect habitat for mosquitoes to reproduce. So we have been using satellite imagery, and we are getting imagery from 4 satellites, Landsat 578 and Sentinel-2. And we are computing different indices that seem to be related to mosquito reproduction. And one is vegetation, water. We're also getting water content in leaves and also water bodies. So basically having lakes or ponds. It's something that we can capture through satellite imagery. And we're also getting burn regions. And so especially in satellite where there's been a lot of wildfires, we wanted to be able to capture that because that could be a negative effect on mosquito abundance. And so we're computing these four indices across 5,570 municipalities for a 7-year period. And so every week we kind of try to get assessment of vegetation and water and burn regions. We also use weather because weather is really important for mosquito, also survival. They can only survive under certain temperatures. And so we captured temperature and precipitation from the Global Surface Summary of the Day NOAA database. And the problem with the weather was that there were only 613 weather stations covering 8.5 million kilometers squared, which is, you know, the whole Brazil. And so thankfully there are mathematical approaches that can help us mitigate that problem. And in this case, we use kriging, which is an interpolation method to basically be able to get data for all the different municipalities. We also got demographic data, and the census data for Brazil is beautiful. I don't know if you have ever, people have had a chance to look at it, but they have a lot of information. They have over 200 variables that they collect on every 10-year basis. And some of the factors that we realized were correlated with dengue included rural population, inadequate sewage, poverty, and garbage collection access. And then finally, Google queries were also used. And it turns out that you know, people go online to find information about dengue, and so that could also be an indication of incidence or prevalence in those regions. So we used 4 different models. We used SARIMA, which is a seasonal autoregressive integrated moving average, SARIMA PCA, which is SARIMA with the variables transformed through principal component analysis. We have the SARIMA PLS, which was using partial least squares, and then STL, which is multiplicative and additive seasonal trend decomposition. And so we use these 4 different models for each unit of space. And so we did the analysis at the municipality level, at the regional level, and at the state level. And here I'm just showing you the results at the state level. And I'm sorry that you can't really see the states, but each of those columns are represented state, and there's about, I think, 27 states in Brazil. So one of the very interesting, and so here I'm showing the normalized error, and it's also very hard to see the numbers there, but basically darker means good and lighter means bad. So it means that you have more error when you have lighter color, and the same for the raw RMA. It's showing you it's darker. Darker means good and lighter means bad. And one interesting result of this study was that, as you can see, there are some states that do better with a specific model. With, you know, SARIMA PCA seems to be doing very well with most of the states, but then there's other states that you need SARIMA PLS or even some that need the SDL model. And this is something that we hadn't necessarily thought about, that one size may not fit all, and that we tend, as mathematicians, tend to use one approach and then apply it to a lot of different areas. And in this case, we've learned that we may need different approaches to address different regions, and that some approaches may do better in certain regions and other approaches may do better in another region. So the one size fits all doesn't apply. And so here is also kind of showing you the predicted and observed results. And the top is municipalities and the bottom is the states. And same here, the lighter means the low dengue burden, and darker means higher dengue burden. And so we basically, we use data from 2010 to 2014 to train our models. And then we use 2015 and 2016 to test the accuracy of the forecast. And we noticed that the model over predicts in areas with smaller populations and clinical infrastructure because they're not really collecting a lot of data. And so one other interesting result, an additional result to the one size doesn't fit all, is that is the data. We also wanted to kind of see the contribution of different data streams on the prediction. And we wanted to, so basically we decided to do see which combination of data stream actually resulting in the best prediction and the best fit for the data that we had. And you can see that some states need all the data. So basically the satellite imagery, the weather, the demographics, etc. Some only need Google and weather data. Some only need satellite and weather. Some only needed the Google data. And some were able to perform just as well with using only clinical surveillance data. And so I think the approach of having different data streams and then utilizing those data streams in the best way to better predict infectious diseases, I think is very important. And so having access to a lot of different data, I think is also important for disease prediction. And now finally, I'm just gonna go into our most recent work, which is on COVID-19. And I kind of wanted to give you first a larger context of where we are. And we're part of a CDC COVID-19 forecasting project that is planned. The goal was to bring together different forecasts of deaths in the US to better understand where models agree and disagree. And then they also wanted to build an ensemble consensus forecasting. And I think, and so here I'm showing the link to that website that is published on the CDC website. And one thing that I feel like we have learned is that if you're looking at one model, you're probably not seeing the whole picture, and that the strength is obtained by combining different models and different approaches, because obviously each model is going to have a different issues or biases. So here's the website to our COVID-19 forecast, which is COVID-19.BSD Gateway. And we have been making publicly available forecasts since early April. We have forecasts for the United States at the state level and for most countries that meet a certain threshold in terms of number of confirmed cases and deaths. And once you click on one of the states or one of these countries, you're gonna see a window pop up that will kind of give you a story of what's going on. First, we start with the situational update, and so you have cumulative cases and cumulative deaths, and new daily confirmed cases and new daily deaths in purple and in pink. And this is just kind of giving you an overall description. And then we go into the forecast. So we are providing short-term and long-term forecasts. So the figures kind of show you the short-term, the 7-day cumulative confirmed cases forecast, and then the tables at the bottom, they show you the 6-week forecast, and so you can kind of see what's happening in either in your state or in different countries. And here, I'm just showing you the results for the US, and I got these screenshots yesterday from our website. We are also providing model performance because we believe that if people want to use our results to make decisions, or if people just are looking at our results to see how well we're doing. I think you deserve to know how well or bad we have been doing in forecasting cases. And so we show you each of those panels are when forecasts that were released. So the first panel here is May 3rd, May 10, May 17, and so on. And so we actually provide the model performance in how close we have been with what actually happened. And in addition to kind of providing that information, we're also letting you know which our forecast is better tracking with. So basically we have three lines, and basically the best case, the middle case, and the worst case. And so we also publish that. In terms of the details, if you go into the model description on our website, it's a combination of compartmental model and a statistical model. This is very similar to what we have for flu forecasting. And so we model how people move from susceptible to confirmed cases and deaths. We are learning the growth rate and the fatality rate from the data. And we have been assuming that the growth rate was going to decline in the future as a result of shelter-in-place restrictions. But obviously, now that many of those restrictions have been relaxed, then our model is going to adjust to those assumptions are probably going to be slightly modified. So one of the strengths of our model is the ability to quickly adapt to situations it wasn't anticipating. This is something that we've learned from the flu, that if you only build a model that is constricted to the past, you're not going to be able to adapt to the future. And so by having a flexible model that can quickly adapt is very important. But the downside of our model is that it can struggle in geographies where little or no data is available. And so that's why we're only producing forecasts for certain countries that have over 100 cases, because otherwise the model is kind of unstable. The biggest challenge with disease forecasting is human behavior. In comparison to weather forecasting, if you bring an umbrella to work, even though people feel that by bringing the umbrella, you're actually changing the weather and it's not gonna rain, that doesn't happen necessarily for infectious diseases. Whatever we do as individuals and as communities are actually changing how disease is spreading. And so whatever, if we wear a face mask or if we take the necessary precautions to reduce our probability of infection, that will have a larger impact in our community. So capturing human behavior in a model is very difficult because there's very limited data that allow us to do that. And here I'm kind of showing the little kid with the pig, and it's, this is a behavior that you could, instead of the parents like removing the kid from the pig, they're like, oh, let's just take a picture. So it just kind of tells you something about behavior and priorities of people. So in conclusion, I feel like epidemic forecasting is still at its infancy, but it's a growing field with great potential. And I really hope that COVID is going to give us that push to take this to the next level and to make this a reality where we're actually using mathematical models with different data streams to forecast diseases around the globe. The challenges for accurate epidemic forecasting are obviously data availability and human behavior, and in both human behavior and also behavior in pathogens. As I mentioned, the flu data, the ILI data that is released by the CDC is usually 1 to 2 weeks delayed. And so if you don't know what's happening today and you're making a forecast that is based on data that happened 2 weeks ago, then obviously you saw how the prediction intervals can become really big. And so the more data that we have and real-time data that we have, the more accurate our predictions can be. Capturing obviously the uncertainties associated with each data stream is also crucial. And especially when you're fusing heterogeneous data into models to derive outcomes that will hopefully be used to make decisions. And so I think that's all I have. I also just want to thank the team that is behind all these models and the work that I presented. I probably don't have some other summer students here, but there's a whole team with many different expertise from mathematics, statistics, computer science, remote sensing, and public health and epidemiology. And I think this kind of work cannot be done just in one field, but it needs the collaboration of many different fields. And with that, I can answer any questions if people have questions.
Okay, thank you, Sarah. That was a wonderful talk. So I have a question that came in on the chat, but I think what I can do, I figured out how to allow people to talk. So so if you do have a question, if you're familiar with the raise your hand, I'm gonna take a question that I got from Lou Gross, but I'm gonna allow Lou to ask himself. Do you wanna
Sure.
unmute and show yourself if you want?
Can you hear me okay, Eric?
I can hear you, yeah.
Yeah, Sarah, thank you very much. It was a great talk. I really appreciate it. There were a couple of questions that came up. One is kind of an overall one. So the approaches that you've described are a compartmental Bayesian host of very great novel data-driven discovery kinds of approaches. I wonder if you would say something about alternative methods and whether or not those might be more appropriate under certain circumstances, particularly agent-based stuff, which of course Los Alamos was one of the founders for the use of in epi stuff. And then a couple of particular questions with regard to the COVID data. So one with regard to forecasting deaths. Do you actually take into account changes in treatment protocols? Because we've been at least hearing some evidence that treatment protocols have changed and have enhanced survivability. And the second thing is, do you or anyone have any data on severity of COVID infection for people who don't wind up in hospitals? And again, here we're talking about anecdotal kinds of information that I think all of us have heard about severity and that people are very, very ill, some fraction, but they're not in any models or data that I've seen. So Sarah, if you could answer those, I'd be really interested.
So answer first your question about agent-based simulations. We are using agent-based simulations for projections, but not for forecasting, because as you probably know, agent-based simulations are computationally very expensive. They run on supercomputers, and it takes a while to tune an agent-based simulation, and also to run like an ensemble of 100 or 1,000 simulations in order to feel confident about the results. So we are currently using for COVID-19 agent-based simulations for projections, and so basically we are exploring, because of the detail of the simulation, we can explore questions that both the SIR and the statistical models can answer, such as what happens when we reopen schools in the fall, and also what happens when more workplaces are relaxing restrictions, and so you can kind of see at a more individual level what's kind of happening in the population, and then hopefully that can help answer the questions that the policymakers need to answer. So that's so I think that agent-based models have a role, but not in the forecasting piece, but they have a role in the projection. The other question was about treatment and how is the model able to capture the different treatments that are becoming available, and how that's changing outcomes, I guess. And so our model is currently not really, we don't explicitly assume anything about treatments. If people are using, if medical doctors are successful in using some of these treatments, then you can, obviously the outcomes will change, and you will see a change in the number of people that are dying. And so our model is based on trends, and so we'll be able to adapt to the changes that less people are dying now because people are using certain treatments that appear to be successful. And then your last question about severity of people, I haven't heard anything about people kind of keeping track of records of severity of people that don't end up at the hospital. I mean, it's already kind of hard to get data. The ILI data or many of the data that we're using is from people that are ending up at the hospital that were tested. And so I think capturing that kind of data would be super important, but I'm not aware of any database that is collecting severity outcomes for people that don't end up at the hospital.
Yeah, thanks. I think that's a major hole that would be great for some monitoring program set up to do. Appreciate it.
Okay, so I think I was wrong about people being able to raise a hand. So maybe there's if there are any other questions, I invite you to post them in the chat. And in the meantime, I've got a question for you about the internet data that you use. It seems like it's potentially prone to noise, like let's say a tweet from the president or an article in the New York Times that, you know, at least for the Google searches, for example. So can you comment on what types of things you see happening that you think are not about infection directly, and whether you filter for that, or if there's anything that it has an influence on?
Yeah, that's a very good question. And that's a problem that we have been trying to tackle for a long time. We call it the Oprah effect, which is, you know, when she had a show, if she would talk about a book, then, you know, everyone would go and kind of look up that book and try to buy it. And so this is the same thing that we've seen with major pandemics. It seems like using internet data is problematic because everybody's searching for that infectious disease. And we saw this during the Ebola outbreak. You know, it was concentrated in West Africa, but if you looked at Google searches and Wikipedia traffic, everyone was looking for Ebola. And so if you didn't live on this earth and you were an alien and you were just looking at the internet traffic, you would have thought that everyone had Ebola, and that's why everyone was looking for information related to Ebola. So what we have found is that we can only use internet data for seasonal diseases, although there's spikes that you see every once in a while. For example, if Taylor Swift or Justin Bieber get the flu and then they post on Twitter that they got the flu, then you do see kind of like a spike in the number of people kind of searching for like, what is the flu or whatever, you know, which is kind of weird. But aside from those, like, you know, minor kind of flukes, diseases that are transmitted on a regular basis that are kind of endemic and are seasonal, they tend to do better. So that dengue is a really good one and flu is a good one. However, if we wanted to use COVID for just to track the incidence, it wouldn't necessarily be good. However, we are trying to use the internet data to capture behaviors. And so what are people talking about? Face masks? Are they talking about, you know, sheltering in place, compliance? And so there's no database that captures compliance, just like, you know, there's no one tracking severity for people that don't end up at the hospital. If we had a behavior database, that would be amazing, but in the absence of that, then we're relying on internet data to help us see the differentiation of how people are using face masks in certain states and not in others, and that can actually help us parameterize compliance in our models.
Okay, yeah, great. That's interesting to hear the way different diseases work.
And the other thing was, so it's good to use two different set of, so Wikipedia is, you know, it's for behavior seeking, or you seek, and then Twitter is when you are broadcasting. If you look at sexually transmitted diseases on Twitter, not a lot of people broadcast that. Like I was just diagnosed with STD, with this STD or whatever, but you can actually find that information on Wikipedia. So that's why using different data, internet data streams is very important.
Okay, thank you. Oh, so we have a few more questions coming in. So, so Jane Wang has a question. Jane, I believe you can unmute yourself.
Okay, yeah, thanks, Eric, and thanks, Sarah. That was very interesting. lots of complexity. I have a relatively simple question that is, a very naive method for forecasting will be just a simple extrapolation. So if I just look at the data and I sort of roughly calculate the growth rate, and I think at least in the beginning when the COVID kind of happened here, for the first month or so, you can use a simple sort of a double every 3 days or something, and you can do a reasonable extrapolation for about 2 weeks. So that gives maybe us a kind of a reference point to think about what are these more complex and sophisticated model, what you're aiming for in terms going beyond that simple extrapolation.
Yeah, I absolutely agree. And I believe the CDC also incorporates a very, moving average type of approach to compare how the different forecasts are doing for the flu. But so yeah, you can probably at the beginning or for a certain period of time, you can actually kind of capture that. But as you so in the different data sets have a lot of different structure that it may not be able to be captured through a very simple model. And so if you are interested in specific targets, the simple models may not be able to give you the answer for those specific targets. And this is because people are trying to prepare resources in hospitals and everything. And so having a more defined kind of target is very important for them. And so the sophisticated models, I believe, are better able to capture the noise and provide solutions to decision makers related to peaks and all that kind of stuff, which I think a very simple model would not be able to.
Right. No, I believe that. So the question is, how long would you expect this prediction forecasting window? Yeah, yeah.
Oh yeah, I haven't tried. I haven't explored the range of up to what point is there a tipping point or a threshold where you are no longer able to capture that. That's a really good question, and I think I will try that and try to get back to you.
Thank you.
Okay, so there are a couple more questions coming in. We're right at 10 o'clock, so maybe I'll just, if we don't get cut off, Artie, Sherman, you had a question, you want to ask yours? And that'll be, I guess, our last one.
Yes, my question is about the Kinza Bluetooth thermometer, which was advertised heavily at the beginning of the epidemic. It was originally designed for flu, and they claimed they were doing better at forecasting than the CDC. So I went out and bought one, but I'm curious to know whether anyone is actually using this data and does it help?
I had not heard about that, and so I don't really know if anyone is using data for that. Yeah. But I will have to look it up because I hadn't heard about it.
Yeah, that's Kinza, Kinsa. Okay.
So I think we've come to the end of our time, and I'd just like to thank Sara again, and on behalf of the entire audience, I'll give a quick applause. We don't have a way of allowing everybody to do that. But thank you for a wonderful talk once again, and I hope to see everybody at our next plenary talk. And don't forget, there'll be mini symposia. They've already started, but I think they're going to ramp up in the next week. So please take a look and see what's going to be coming soon.
Thank you very much.
Great, thank you.